follow a pattern. Within a row, like for the first row, hydrogen and helium, it starts low and goes high. The next row is lithium through neon. Starts low at lithium and goes high to neon. Then the next row starts low and goes high. Now you can tell that the trend is not absolute. There's kind of a dip right there and right there. Why the dip? Well, that's what we have to talk about, why that is. Well, we'll get there. What? They did. Yeah, they talked about electron repulsion for some of those. Yeah.
Is sulfur higher than phosphorus?
They're about the same. It looks like, well, yeah, it looks like it is kind of jointed upward a little bit. But
Why is that?
I don't know. The book has an example. It was in the reading assignment, and it said that sulfur is just a little bit less than phosphorus. All right. Now, what elements have a high ionization energy? Well, ionization energy is going up here, so what do the high ones have in common? Those are the noble gases. We're talking about trying to remove an electron. Noble gases have the most stable electron configuration. That means it's going to be difficult to remove an electron from. Stable means resistant to change. What elements have the lowest ionization energies? Yeah, the alkaline metals, the first family. Yep.
Wait, so if you did remove an electron from a noble gas, would that be like really?
No, it can be done.
No,
Several.
I mean, would you create like a really
You'd make a noble gas ion. You'd make krypton with a positive one, or argon with a positive one.
Would there be something like very special to it? Or like,
Yeah, it would be very unstable as that, and it would tend to react to get that electron back. It's not going to make a permanent bond, but it'll try to get the electron back. Alkali metals have a very low ionization energy. They're there down at the bottom. That means it's easy to remove an electron from those low elements. Yeah, it still does take energy. You still have to put energy in, though, to get them to remove an electron. You okay with that? Okay, moving on. This is very common, too. When you see data like this, you can have successive ionization energies where you take one electron off, then you keep hitting it with higher energy of light and get another electron off. Then hit it with it, get a higher energy and get another electron off. So you can have multiple ionization energies every time you're losing the next electron. Notice that every ionization energy takes more energy than the one before. And then notice that eventually you get to a point where you have a big jump. 735 for the first, this is magnesium. So to get the first electron off, it takes 735 kilojoules. Then after that, you got one electron taken off. Now it's always going to take more to get the second electron off, because it now has made a positive one ion. Those remaining electrons have been drawn in more tightly to the nucleus. You have to add more energy to get the next one off. So that's why the second one's always higher than the first. That's true down here too. For magnesium, taking the third electron off is a lot more energy than taking the second one off. Not just higher, like this is higher than that. This is a lot higher than that. That big jump. Why would that be? For taking the third electron off of magnesium West. That's right. Once magnesium loses 2 electrons, now it has lost its second energy level, and it's now back to the, I said second. It has lost its outer energy level. It's back 1 to a noble gas arrangement. That's very stable. Now if you want to take an electron off, you're going to have to work for it. So anytime an atom has enough electrons taken off to get it to a noble gas arrangement, the next electron is going to be very difficult to remove. Where is that for aluminum? 580, 1800, 2700, boom, 11,000. So you see that after 3 electrons come off for aluminum, now take, after 3, that has gotten aluminum to the same electron arrangement as neon. Now try to take an electron off after it has gained a double gas configuration is going to be higher. It takes a big amount of energy compared to the other. Yeah.
Is there a reason why aluminum for ionization energy is bigger than magnesium?
Yeah, because aluminum has 13 protons, magnesium only has 12. And it's got one more electron that you have to pull off of it. So you've got 13 electrons holding on to 10. 13 protons holding on to 10 electrons, where magnesium has 12 protons holding on to 10 electrons. It's going to take over. Okay, we good with this slide? So let's move on. I try to keep moving with this because it's kind of boring. This is the slide that talks about the exceptions. I want to cover these up so Amber doesn't peek.
What?
Huh? So as we go across a row, the ionization energy is generally going up. The reason for that is because atoms are getting smaller as we go across a row. The effective nuclear charge is going up, which means that the outer electrons are feeling more and more positive charge, drawing them in closer as we go across. That makes it more difficult, meaning more energy is needed to remove an electron. What is it about nitrogen and oxygen? Did you read that part in the book? Mina, what did it say?
There's one in each orbital or whatever.
For which one, nitrogen or oxygen?
Nitrogen.
Okay.
When so like each orbital has one in it. When oxygen is like one more. So
Yeah. Nitrogen, this is exactly what you're saying.
yeah.
Nitrogen has 3 electrons and 3p, 2p. So each of those electrons is spread out from the other electrons, only 1 electron in the orbital. It takes a certain amount of energy to remove that one of those 3 electrons. We don't really know which one. We assume like the last one right there. That one comes up. For oxygen, that down arrow is the last electron. So if oxygen is going to lose an electron, it's going to be that electron right there. Now, because oxygen is such a small atom, it has a lot of repulsion. These 2 electrons are kind of fighting to get away from each other. So because of that, this electron is going to be easier to remove because of the quarreling between those 2 electrons that are pushing away from each other. So oxygen, even though it's farther right, because you got that quarrel there, it's going to have an easier time getting rid of an electron. That's why we have this dip, this fall. Only for oxygen and nitrogen. When we go from oxygen to fluorine, now we have 2 pairs. And you say, well, even 2 pairs, that's going to have even more repulsion in there. But what happens is, because fluorine's nucleus is more positive, that it really helps to keep those electrons in and not as willing to give off. Now, what about the dip from beryllium to boron? And we see even a bigger dip from magnesium to aluminum in the next row. What's going on there? Well, beryllium and magnesium have just finished an s orbital, or s sublevel, and now, going to the next one, now the atoms are starting a new energy sublevel. They're farther out from the nucleus, and because they're farther out and kind of shielded from the nucleus by those inner electrons, they don't have as much of a pull on the electrons. So that's what it is with the oxygen and the boron. Boron it's a lower ionization energy than Be, and that's because Be just finishes the 2s. Up to 2s, those electrons are kind of shielding the nucleus from that 2p electron being able to feel.
And it doesn't want to keep the 2p one, or doesn't give it up.
Right. And the reason it doesn't want to hang on to that 2p is because that 2p electron doesn't feel the nucleus as much. So the shielding effect, when you get a few energy levels and sublevels piled up on top of one another, that cause the outer electrons not to feel the nucleus as much. And so that will dictate a lot of these properties, the whole shielding So that's the big deal about ionization energy. Yeah.
And then why would it take the energy to give off like lithium electron? Wouldn't it give off energy? When it breaks?
This is not lithium reacting with something else. This is just pure lithium vapor, and you're firing electrons. You're firing photons at it to break the electron. So yeah, that is an endothermic process because there's no other atoms involved. If you have lithium and oxygen together, lithium's willing to give off electrons, oxygen's willing to take electrons, so that would be an exothermic process. But when you just have lithium there, you have to put energy in. Because spontaneously it's not just going to lose an electron. Okay? All right, so the trend down a family, what we find, if you look at the noble gas, you got helium, neon, argon. They're tending to go down. The same thing happens with the lower ones, lithium, sodium, potassium. It's not as pronounced, but it's also got a negative slope. Down a family, because the atoms are getting bigger and the outer electrons are farther with the nucleus, it always takes less energy to get the electron off the bigger atoms. That's really what this is saying. Bigger atoms takes less energy to an electron. We only have 2 more nights before the quiz on Thursday. It's a good idea, if you haven't started your homework yet, to not wait until the day before. You will find, if you've started, they're not bad. They go pretty fast. And I think this may be the easiest chapter of homework we've had so far, if you haven't started yet. You'll be surprised. What's that? Not for those that don't do it on the day. I'm not blaming anybody.
So we're looking at lithium oxide, and on Alibaba.com, they have this huge, huge box of lithium.
Wow.
It says lithium minimum order 25 metric tons.
Oh my gosh.
Oh, shoot.
Okay, let's get through electron affinity. I've got 2 slides for electron affinity. All right. I have a ruler here that I'm going to put on the 0 line. Electron affinity is kind of weird because values can be positive or negative for electron affinities. The only periodic property that can be positive or negative. Ionization energy is always positive. You've got to put energy in to get any atom's electrons off. But this one, now take a look at what the definition is. Electron affinity is the energy change, and we had this on our reading quiz, the energy change when an atom gains an electron. Some things are not favorable for gaining electrons. They'll have a high electron affinity, a very positive. Some things are very interested in gaining electrons, like fluorine and chlorine. They'd love to gain an electron. They have a very negative electron affinity. What? No, that means energy is given off. So these would give off a lot of energy, and the more energy given off, the more stable the product is. So electron affinity is about gaining an electron, which is the opposite of ionization. That's about losing an electron. So down here, is what I was talking about. The values that are negative, those are elements that tend to form stable -1 ions. Yeah.
So do we just go most of the time that left to right they become more negative? We just assume that?
No. Because here's the 0 mark, right above